This video is the second one on RSquared, so we're going to dig into some of the details with Excel and computing this R-squared value for a particular data set. So you can see here I've got, in the linear example, which is what we're going to start with, I've got my data points xi, yi. So you can see I've got all of those there. That's my original data set that I'm starting with. I've calculated xy and x squared and the sums of all of these, right? Remember, we need all of those to find the regression line. And so then from that, I found the regression line, which is y equals 2.278 x minus 3.2. So that's my m and my b, okay? So I've got all of that. I found all of that. And the reason that I needed to first find the regression line is because if you remember from the definition of R squared, we needed to know the predicted values, and those come from the regression line. So if you look at the predicted values, y hat, what that is it takes in an x value and it plugs it into that regression line. So m times that x value plus b, and that gives me the predicted value. So if my x and y values, if my values were exactly on the line, rather than having y equals 2.4, because the line is 2.27x minus 3.2, when x equals 1, we expect y to actually be negative 0.92. So that's actually fairly far off. You can see some of the other y values are closer. So for example, we predict a y value of 5.91 when it's actually 5.7. So that's not so bad. And a lot of these in the center are actually closer. Okay? So I've got my x values and my y values. I've got my predicted y values. And then I calculate these residual, regression, and total terms. So if you remember from the previous lecture, the residual term is the predicted value minus the actual value of y. Okay, so that's what that is. The regression value is the predicted value minus y bar, minus the mean. So that's where that comes from. And then the total value was y minus y bar. Okay, that's the total variation from the mean. Okay, and so all of these get squared, and then we add them up. These are actually our sum of squares terms. So the sum of squares residual is 85.5. Sum of squares regression is 428.18. And the sum of squares total is 513.7. Okay? I didn't say this in my lecture, but you'll see if these, if this predicted values are actually the line of best fit, the residual and the regression should add up to the total. And you can see here they do. 85 plus 428 gives us 513. Okay? That will only happen if your predicted values are coming from the line of best fit or the curve of best fit. So be aware of that. Okay? So once we've got that, we're going to take regression, sum of squares regression, divide it by sum of squares total, and we get an R-squared value of 0.83. Okay? So of the variation from the mean here in our y values, 83% of the variation is predicted by the regression line. The other 17% is kind of unexplained. And this is kind of on that boundary edge. 83% isn't great. It's not terrible either. Okay, so in the future, we'll talk about kind of deciding whether the line is a good fit. Okay? But what I'm going to talk about, the other example I want to talk about today is you can actually do this in a nonlinear situation. Okay? So if you look at this data that I've got down here, so I've got x values 1 through 10, y values, which range from 1.5 to 92. If you look at a graph of this, which I'll put in right now, this data is not linear, right? This is fitting some sort of parabola. And so what I've done is I've actually gone through and I've found the best parabola to fit this. So something of the equation y equals ax squared plus bx plus c. Okay? And I've done that using Excel's multiple regression tools. That's all down here. If you look at the bottom of the spreadsheet, if you've seen some of this before, you may recognize this. But basically, the coefficients are right here. So what this is saying is that the parabola of best fit is y equals negative 3.87. So that's that number there, plus 2.557. I'm not going to write the whole thing down. X coming from there, and then 0.7038. 0.7038 x squared. Okay, so that's the parabola of best fit. And so the same way that the line of best fit gave us predicted values, we can use that parabola of best fit to get predicted values y hat. And that's exactly what I've got here. You can see that I've taken those coefficients, D48, D49, and D50, and I've taken D48 plus D49 times x plus D50 times x squared, and that gives me my predicted values. And just like we did before, we can find the residual, right, which is the y, the actual y minus the predicted y, the regression, which is the predicted y minus y bar, and the total, which is the actual y minus y bar. Okay? We can take those, we can square the differences, we can add up, we get our sum of squares residual, sum of squares regression, sum of squares total. Since these came from an actual curve of best fit, was our predicted parabola of best fit, you can see again, residual plus regression adds up to total. If that doesn't happen, that means that your y hats are not coming from a model of best fit. And so that can be a clue that you've made some mistake somewhere with the y equals mx plus b with your regression. Anyway, in this case, we get r squared of 0.9939, very, very high, very close to 1. You can see that actually also appears in what I already got from Excel. I'll explain how I got you this table down here from Excel that has all of it in here in a little bit more detail in the future when we talk about fitting nonlinear curves. Okay, so in our next few lectures. Okay, so that's how you can calculate r squared using Excel and even in nonlinear situations.